Hello everyone, welcome to ECE 475 first session tutorial. My name is Milad Antezami. I'm your TA in this course. I'm a first year PhD student in CR's Antenna group. I hope to have a joyful time together and everything goes well with you in this course. As you know, the main goal of this course is to help you with designing antenna. We are emphasis on a practical aspect of designing antenna instead of going through the theoretical aspects. The project is the important part of this course and it will be designing antenna in HFSS. Today in the first session of tutorial, I will introduce the HFSS to you. We will take a look at finite element method which is employed by HFSS. We will see some features and capability of HFSS and some general design procedures. At the end of this tutorial session, you will be familiar with at least how to build the structures in HFSS, how to build the boundary conditions and excitation and some solver settings. The HFSS is a full-wave electromagnetic EM software package for calculating the electromagnetic behavior of a 3D structures. By using HFSS, we can compute basic electromagnetic field quantities for open boundary problems, radiation of near field and far field, the IDEM modes, and resonance of structures. We can compute a port characteristic impedance or propagation constants like gamma. We can compute and generalize S parameters and S parameter renormalize. We can de-embed the S parameters. We can renormalize it to a specific port impedance. High frequency structures similar to HFSS is a 3D EM simulation tool which helps us with designing a broad range of high frequency products such as antennas, filters, and IC packages. HFSS has advanced 3D electromagnetic field solvers based on finite element methods and other integral equation methods that we can learn more in detail in numerical method course in EM course. As you know, there are lots of capability and features to HFSS. It has advanced ACIS-based modeling. It has a true parametric technology, dynamic editing. It has a very powerful and efficient report generation. As you can see the dynamic field visualization in the HFSS. You can design a flow automations, optimetric, sweep parameters, and whatever you want. Another feature of the HFSS is the advanced material type. You can define a frequency dependent materials. As you know, the permeability and the permittivity of the material change through the frequency. You can define a nonlinear material like phase change material, PCM or MEMS. You can define an anisotropic materials. You can define any boundary condition you want in radiation or perfectly matched layers. RLC layer impedance, infinite planes, finite conductivity, and symmetry planes. You have the features of the advanced solver technology like automatic conformal mesh generation and adaptive mesh generation, which is the important and key role in the HFSS design to have adaptive mesh generation, and you don't need to care about your mesh structures and mesh settings. Common HFSS application in antenna design, microwave design, and signal integrity design. In antenna, you can design and simulate planar antennas like patches, dipoles, horn, conformal cell phone antennas, spirals. You can design waveguide structures You can design a wire structure like dipole and helix antenna. You can design an arrays structure like infinite arrays, which is attractive features of HFSS, frequency selective surface, and photonic bandgap structures. Also, you can calculate and simulate the radar cross-section of every structure you want. In microwave design, you can design and simulate the filters structures, EMC, connectors, waveguide, silicon, CMOS or BiCMOS like spiralized inductor and transformer. In a signal integrity design, you can modeling the package, PCB board, connectors, and transition that give you the degree of freedom to know the structures. The HFSS gives you the matrix data, as you can see in these pictures, in S parameter, Y parameter, and Z parameter. We will talk more in detail in a few sessions or in these sessions. The HFSS give you the capability to export your data in every in like touchstone data tables. You can use the STUPI file in and you import it in MATLAB or in ADS to design an active antenna. You can use a graphical output format to see the plots, field plot or as parameter plot and whatever you want, and so on. The common display format of the HFSS is a rectangular and polar one, and you can use the Smith chart to show your result and data tables also. In HFSS, you can see the fields, electric fields, you can simulate and see the magnetic fields, you can see the surface current and volume current, you can calculate the power or a specific absorption rate. In a radiation criteria, you can calculate the 2D or 3D far field or near field radiation and radiation of the arrays, regular or custom setups. You can see and calculate the RCS. The common display format is value on surface vector on 2D report, and you can see the radiation field in a common output format like animations, AV or GIF file or data table or graphical one, as you can see in these figures. The numerical techniques used in HFSS is the finite element method, FEM. In this method, a structure is subdivided into many small subsections, which is called finite elements. In HFSS, these finite elements are in the form of tetrahedra. The entire collection of tetrahedra construct the finite element entire mesh. As you can see in a meshing scheme, 2D triangles for the planar structures and 3D tetrahedra for 3D structures. The components of a field that are tangential of the edges of an element are explicitly stored at the vertices, as you can see here. The component of the field that is tangential to the face of the element and the normal to an edges can be explicitly stored at the midpoint of the selected edges, and the value of the vector field at the interior point can be interpolated from the nodal values. To satisfy the Maxwell equation, the tangential field of the electrical field should be the same and should be continuous. I briefly can describe the solution, but if you want more detail, I can theoretically explain it during office hours. As I say, these fields are connected and related to each other, so the Maxwell equation should be satisfied. And once the field solution is found, we can generalize and we can produce S matrices solution and so on. It's clear that the source of the solution should be in the terms of the electric field or in terms of the magnetic field rather than in terms of the voltage and currents. And by using the FEM, the integral equation of the wave progression transformed to the matrix equation, and we can solve the matrix equation to get the result. As you know, the main performance of the HFSS is to derive and construct the finite element matrices by using the field equation and calculate the field and S matrices, which is related to the ports and excitation ports that we define. I can briefly the procedures of the solving the problem in HFSS. It's one when you create geometric structures and you represent it by a finite element mesh by using the tetrahedral elements. Then testing functions are defined for each tetrahedron. So it's resulting in 1,000 or million thousand of testing function. This field's equation is multiplied by this testing function of each mesh section and integrate over all the solution value. By this method, we can solve each structures of the HFS in HFSS or in other software which. As I discussed, this is the tangential vector finite elements, which is used here, is expected to solve for vertex, edge, expected to solve for faces. It should be interpolated with these three nodals. Electric field, the transfinite element method is used for the planar structure. That can be, if you want to more detail, you can refer to this article. But the most important thing in HFSS is adaptive meshing. As you know, the field solution process in HFSS is iterative. In the other words, HFSS use the processing that I defined repeatedly by refining the mesh in an intelligent manner until the correct field solution is found. This repetitive process is called an adaptive mesh refinement process. That is result in a highly accurate simulation and results. Automatic adaptive mesh refinement is a critical part of the HFSS for all of our solutions, and it's to produce the accurate results. These meshing techniques help us to focus on setting up our design effectively and efficiently rather than spending so much time in determining and creating the best mesh for our structures. As you know, the adaptive process meshing, as you can see in this pictures or figures, is the HFSS generates an initial geometric conformal mesh, and then by using the initial mesh, HFSS compute the EM field that exists inside the structure when it's excited at the solution frequency. So based on this current finite element solution, HFSS determines the error of the solution, and then by a predefined percentages of the tetrahedra in this region, the mesh can be refined by creating a number of smaller tetrahedra. that replace the in an original RAR element. HFSS procedure is like that. It's solving in an initial and then analysis the error and then refining the mesh, and this process occurs until the convergence criteria are satisfied. The requested number of adaptive process is complicated. Now we are going to features and capability of the HFSS. By HFSS you can accurately have a full wave EM simulation. You can import and export of the 3D structures from like Cadence software. You can import the by CMOS or CMOS technology or integrated circuits, or you can use the solid states and create your antenna mechanically and then import the 3D structure in the HFSS and then run the EM simulation, and you can automatically use adaptive mesh generation and refinement and use adaptive sweep for a fast frequency sweep if you have using the ultra wideband antenna design. You can inclusion of a skin effect of your structures and losses, and also you can use the feature and capability of a direct and iteratively matrix solvers and item mode matrix solver, which is critical for resonance frequencies. Also in solution data visualization, HFSS has a feature to get US parameter, Y parameter, Z parameter, and you can see the 2D plot, Smith charts, port characteristic, impedance, current, E field, H field, 3D statics, and animated field, plot in a vector display or magnitude display, copole or crosspole. You can far field calculation, 2D, 3D gain and the realized gain, radiation pattern, directivity, material losses. Let's go to the HFSS desktop by using a cat pass and by double click on for ANSYS teaching access. You can open the HFSS desktop and you can see here is the ANSYS electronic desktop 2020 revision 1. By clicking on HFSS, by selecting the HFSS, you can open the HFSS file under your project name. Here is HFSS design 2 driven model. So in HFSS desktop we have a project manager windows which contains a design tree which lists of the structure of your project, message managers that allow you to view any errors or warning that HFSS gives you and aware you to fix it, property windows that display and allow you to change the model parameters or attributes, a progress window that displays the solution progress, a 3D modeler window which contains the model and model tree for the active design. Here is the see the HFSS is the menu bar, toolbars, project managers with the project trees, project managers with the project tree in the new version, and these are properties of the what you create in the this windows, which is the 3D model windows, is a progress windows and message windows. Status bar, which help you to understand what state you are, is a property window, progress windows, and the coordination entry fields that we will talk more about it in when we creating the subject and we want to unite it, or we want to duplicate it, or we want to copy of it. The project manager windows, which consists of our project names, our design, HFSS model 1, our model, our boundaries, excitations, mesh operations, analysis, which is the part of the design setup, design automations, optimetrics like parametric sweep, optimizations, sensitivity, and statistical. And after our simulation is done, we can go to the design result, port field display, field overlayers, and radiation, and be finished. Here is the property windows, which characterize or properties of our models, which is name and box 1, the material, which is the vacuum. We can check to solve inside the model. We can set the orientation of the model, which is a global. We can display the model with we can change the color, or we can transparent the model. Ansoft 3D modeler windows is a graphical area. You can see our model, our box, and you can see the design tree, our model, which is box 1. We can create a box. This is our coordination system, Z, Y, X. It's a global. These are our planes, our points, or list of our objects. This is the coordination systems, origins. This is the face that we can select it by pressing Ctrl with F. This is our H, which can select it by pressing Ctrl plus E. We can select the object by pressing the Ctrl plus O, and that's it. Also, you can right click on the model and you can measure the edges, measure whatever you want. You can change the view. By the way, by pressing Ctrl plus D, you can have a fit view of your structures. Here is the 3D modeler design tree. You can see our model, for example, my ring, my Teflon, or not assigned material, and objectives. You can see our PEC structures. It's our object, it's related to our material. We can change the material. I will show you how to change the material, how to assign a material, how to define a material if you have a new material, or how to define a model-based material if you need it, or if you need to use a nonlinear material, you can define a nonlinear material, and so on. Now we can go to HFSS windows and create some box with now we are going to general design procedures for an antenna design structures. First of all, you need to set up or define the solution types. Then you need to parametric model, geometric, assign material. Then you should assign boundary conditions of the structures. Then you need to assign excitation, wave port or lawn port. Then you should set up the analysis setup, the solution setup, and you should define your frequency sweep, and then you should check your and run your solutions. During the analyzations, it begins with an initial mesh and it solves if it converge or not. Then the mesh will be a refinement, and after the convergence goes to the specific error box. specific error ratio, then the simulation is finished and the result would be updated. Your result, the 2D reports or electric field of your result would be updated. Here you can see the design steps. First of all, you need to choose your solution type. Then you should design your model using your toolbox, creating a box, creating a sphere, whatever you need. After that, you should define excitation, wave ports or alarm ports. We will discuss about it in a few minutes. Define your boundary conditions, define your solution setup, add frequency sweep, and if you need it, define optimetrics, parametric sweep, optimization, or tuning sweep. And then you check the solution and run the simulation. After the running and then the simulation was finished, the running of the simulation, you can view the results of the S parameter, impedance, field, radiation pattern, and etc. of the structures. As I said, before creating the design, you need to specify the type of the solution that you want to HFSS to calculate. The solution type defines the type of the result, how the excitation are defined, and the convergence. These are the following solution type are available. Driven model calculates the model-based S parameters. The S parameter solution will be expressed in terms of the incident and reflected powers of the waveguide modes. Driven terminal calculate the terminal-based S parameter of a multi-conductor transmission line ports. Idem modes calculate the idem modes or resonance of the structures. How to convergence the driven model. The delta S for the model S parameter, which is the delta is defined as the specific error box or error limitation of the S parameters model. So it's for a driven terminal, delta S for the single-ended or differential nodal S parameters, and idem mode delta F. To set up the solution type, you need to select the menu item HFSS and then select on the solution types and choose one of the following: driven model, driven terminal, idem modes. Like this, you can choose HFSS and solution type. Model, idem modes, terminal, characteristic mode, which was this feature for the new version of HFSS, transient, and SPR. So here is the question that what's the difference between modal and terminal solution types. For example, if HFSS is used to model a pair of a coplanar or parallel macrostrip transmission lines, a driven model solution yields a result in terms of the even and odd modes that propagate onto the structures, while driven terminals mode solution generates the common and differential mode result. There are two different kind of the result that would be created by these solutions. Before creating the model, you should set the model unit. To set the units, you should click a modeler and then go to the units tab to set the model units and select the units meter or something else like this. Go to the modeler and units. Second units is millimeter. Also, here is the toolbars that you can customize for yourself. There are lots of things in the toolbars, lots of windows. You can create the material, but this is the I think HFSS 2015, but for 2020 the HFSS will be different. There is a view tab. You can manage the view of your structure. You can draw the structures, draw tab. There is a structural subjects. There is a model tab. There is a simulation tab. There is a result tab, and there is an automation tab that help you to create your model and simulate with HFSS. In the Draw tab, you can create the 2D draw objects like line, spline, arc, equation-based curve, rectangle, ellipse, circle, a regular polygon, and equation-based surfaces, like you can see here. And you can also create a 3D objects like box, cylinder, regular polyhedron, cone, sphere, torus, helix, spiral, and bond wire. Now we are going to create a box and assigning materials to the R box. Go to the draw, creating a box, just drawing a box like this. You have a box, but by double click on the creating a box, the box window will appear here, and you can position the box and have X size, Y size, Z size. And what's attractive for the HFSS and other simulation softwares, that you can define a parametric one, like parametric like minus sub x divided by 2 minus sub y divided by 2 and 0 are our starting position, and then we can define our x size. Before we should define sub x. Millimeter is a length, its value say 5 millimeters, sub reg. Now you can assign a material to your box. By right click on your box, you can assign materials. In assigning material, you can search the material by name, like if you want to the box be PEC, you can select PEC. If you want to copper, you want to have a dielectric one like Rogers RO403 or FR for epoxy. You can also add a material if you know the permittivity of your material. You can define your material like relative permittivity, relative permeability, and also you can tangent, loss tangent, also dielectric loss tangent here. Also you can have a lots of options to define your material based on the model of the material, based on the nonlinearity options of the material, and so on. Now I select FR for epoxy for this box, so the vacuum is changed to FR for epoxy. Also in the properties box, you can see the box name, your material, or you can check the solve inside, orientation, you can check the model, the group model, you can also change the color of the material. Also, you can have a transparent material and see the origin of the coordination. So after designing your structures and creating your model, you should defining your boundary condition and excitation. This is the important step because of the majority of HFSS errors are related to improper usage of excitation and boundary condition. And to reduce the infinite space to finite volume, HFSS apply a PEC boundary conditions to surface surrounding geometrical model. Any exterior face of the model geometry not given user-defined boundary condition is assumed to be a perfectly E-boundary. So boundary condition can be used to reduce the solution time and computing resource demands. Ports are a unique type of a boundary condition. Ports can allow us to allow the energy actually to flow into and out of the structures and define on the 2D planar surface, and the 2D field patterns serve as a boundary condition for our full 3D problems. There are two common port types in HFSS, like wave ports, which is the external port, and lumped port, which is internal port. Waveport arbitrary port solvers calculates the modal analysis on the surface of the 2D structures or waveport, and it assumes a semi-infinitely long waveguide with the same cross-section of our structure and material properties as a port surface. This port is recommended only for surfaces exposed to backgrounded objects. Usually they are used to excited transmission lines like microstrip, strip lines, coplanar waveguides, CPW transmission lines, and waveport can give us S parameters, Y parameter, and Z parameters, characteristic wave impedance Z0, and the propagation constant gamma. The waveport can support multiple modes, and it has a de-embedding capability and renormalizing capability, which has a important feature to designing antenna filters and some other things. All other edges are assigned perfectly E-boundary by default, so the waveport should be backed by a piece or conducting objects. A waveport excitation should be applied only to an other face of the solution space. HFSS at first calculated 2D solution for the waveport, and you can see it before you running the HFSS simulation, and uses these modes, this model analysis to solve the source. It used this analysis as a source for the 3D model. With a waveport, the port is defined within a waveguide. Simple setup for encoded transmission line like a coax waveguide and etc. The challenging setup for unbalanced or non-closed line like macrostrip or CPW. Here you can see the waveport and how the energy goes through the transmission line. We should notice that the waveport should be creating too close to a current carrying line, and to allow the transmission line or to allow the energy coupling from a trace to port 1. And because of this concept, the wave port should be a large sidewalls. Here is the finger rules for a microstrip port height and width for the wave port. Also, if you have a microstrip line with the width of the W and the height of the substrate H, the microstrip wave port height should be 6 to 10 times of the H, and microstrip port width should be 10 times of the W if the W is larger than H, or 5 times of the W in order to confine the energy into the transmission line. Also, here's another rules for the CPW line, which the waveport height should be at least 4 times of the H or G. G is the gap, or S is, or H is the height of the substrate. Also, port width should be 3 to 5 times of G, or 3 to 5 times of the S, the width of the line. Here you can see a lumped port. It's recommended only for a surface internal to model. You can see you should create a sheet, and you should assign a boundary and a launch port to this sheet. And this sheet is excited by a uniform electric field, which by characteristic impedance which user defined one. You can see the dipole element with a lump port, and you can see a microstrip line internal port here. There is some advantage and disadvantage of the lump port. It's excite a single TEM mode with a no dim bending features. It allows us to have a uniform electric field on a port surface. It could be normalized to a constant user-defined characteristic impedance Z0, and that's it. Here is a circuit model of the lumped port. There is a difference between a wave port and lump port. For a lump port, a parameter normalized to user-specific characteristic impedance, single mode propagation, no de-embedding operation available, and must be located inside the model. For wave port, the S parameter normalized to computed characteristic impedance. You cannot define the characteristic impedance. The multiple propagation mode possible through the wave port. The embedding feature available as a post-processing operation. And what's the important feature of the wave port? Must touch a background object, or as I said, must be backed by a conducting or PEC object. So here's another view from the differences between a wave port and lump port. Accessibility, external faces for the wave port and internal to model for the lump port. High order modes is available for wave port but not available for lump port. The embedding feature, as I say, is available for wave port but it's not available for lump port. Renormalization is available for wave port and also is available for lumped port. Setup complexity is moderate for wave port, and it's the setup complexity is low. It's easy to set up the lumped port. Now we should defining a airbox radiation boundary. What's the radiation boundary and what is used? It used for creating an open problem in HFSS that allow electromagnetic field to radiate infinitely far into space in the case of the antenna design, and there is no back propagations of the boundaries. So in HFSS, it absorbs the wave at the radiation boundary, and so it also radiation boundaries apply only on the outer phase of the solution space. And when simulating an antenna, we should place the radiation boundary approximately at a quarter wavelength away from any radiation surface. As the tutorial material said, is a use for a far-field radiation boundary lambda over 8 of the lowest frequency in all direction, but I say as my experience, it's for non-radiation direction. It's good to have a lambda over 8, but it's good for lambda over 2 or lambda over 4 away from any radiating surfaces. The more airbox or the larger airbox you have, the more solving time you should spend on solving this airbox, because the HFSS solve the electromagnetic Maxwell equation and mesh the volume inside the radiation box, and that's because I will show you how to defining a radiation box in HFSS, but for now, if you you can draw a airbox, go to the HFSS radiation tab, insert a fall fit setup, and select on an infinite sphere. By right click on the airbox, you can go to the assign boundary and radiation box. All the faces of the radiation box will be perfectly matched, and there is no back propagation of this. Also, to create a radiation boundary, you can right click on the radiation tab, selecting infinite spheres, and infinite spheres 1, you can set up the phi and theta. The theta is started from minus 180 to 180 by the step size of 1 degree, and phi is going from 0 to 180 by step size of 1. Also, you can set a solution setup and frequency setup by clicking on analysis and add a solution setup. You can have a driven solution setup. It is enabled. You can set the solution frequency, maximum number of pass, and maximum delta energy. This is for adaptive solution to adaptive mesh refinement, the maximum number of passes that the HFSS should use to refine the mesh, and the maximum delta energy is using to set our error box. Also, for the option for the driven solution setup, you can specifically define the minimum number of passes, which is in a default is 1, your minimum conversion passes, or solution option that I will talk a little bit more about it in a few in the next sessions. Also, in a frequency sweep setup, you can add a sweep frequency by right click on the setup and choosing add the sweep. There is three sweep types: discrete, interpolating, and fast. Discrete solve at each frequency. You can save an electric field at each frequency. You can save a radiation pattern at each frequency. Fast sweep type is used for narrowband simulation. If you don't want to see the radiation, E field, or surface current or something like that, and your frequency band is narrow, it's better to use a fast sweep type. Interpolating used for wideband simulation, and again, if you don't want to use a radiation pattern, and if you don't want to see the electric field or surface current, and your frequency band is wide, if you just want to see S parameters, Z parameters in a wide range of the frequency, it's better to use interpolating. For running the simulation, first you should save the project, and then you should validation check. Here is the sign of the validation check, and after all the thing is okay, you can select the analyze, and in the progress you can see the setting up the simulations. In the result you can see S parameter, radiation pattern, 2D and 3D. I will be clearly set an example to clarify the issue and clarify the process to see how to designing the antenna with HFSS. Is a simple one, and also in a result you can create a model solution data report like rectangular plot, rectangular scat plot, polar plot, Smith chart, and so on. In a trace tab you can select on S parameter S11, which is a function of the dB, and you can create a new report which a primary sweep on a frequency. Here is the example of S parameter, which is designing and solving with HFSS, and you can see this parameter is for dB, and it's going from 1.5 to 2 gigahertz. If you want to viewing the result and radiation pattern in 2D or 3D, you can just clicking on result and create a fall feed report, then clicking on radiation pattern and defining what plane that you want to see the pattern, E plane, H plane, whatever. If you want to see the pattern or gain or directivity, you can use the function of the dB gain, total gain, realized gain. I will be explicitly in the next tutorial session we will talk more in detail about this feature of the HFSS. Don't worry about this right now, and there's a lots of difference between a gain, total gain, realized gain, directivity in dB and so on. Here is an example of a radiation pattern, 2D radiation pattern of a I think the patch antenna. Yes, it's a patch antenna because the gain is about 3 dB. And here is the 3D radiation pattern. The HFSS helping us to see the 3D radiation pattern. For next lecture, we will take a look at optimetrics item mode solver, some model design tricks, some tricks in plotting fields, and antenna example. We will explicitly, we will clearly show you how to design an antenna, how to figure this parameter, and how to see the radiation pattern in 2D or 3D plot. And for today I want you, so at the end of this lecture I want you